The cheetah is a true marvel of speed. Known as the fastest land animal on Earth, it can reach speeds of up to 60 miles per hour in short bursts. But what if this amazing creature found itself in the unique environment of a space station? How would its speed change in a microgravity environment? Would the cheetah still be able to run as fast, or would the laws of physics in space slow it down? To understand this, we must first explore the forces that allow a cheetah to reach such incredible speeds on Earth. The cheetah's acceleration is truly impressive, able to go from 0 to 60 miles per hour in just 3.4 seconds. Its slender aerodynamic body is designed for explosive bursts of speed. The cheetah's powerful leg muscles are built to propel it forward in rapid, coordinated movements. Its spine is highly flexible, allowing it to stretch out during each stride. On Earth, gravity pulls the cheetah's body toward the ground, providing the necessary traction for its acceleration. But in space, gravity is much weaker. The microgravity environment on the International Space Station, ISS, means that objects, including animals, experience very little gravitational pull. In microgravity, the normal forces that help animals move quickly, like friction and gravity, are significantly reduced. So, what would happen if a cheetah tried to sprint on the ISS? Without gravity to push against, the cheetah would struggle to generate the same traction it has on Earth. Cheetahs rely on their claws digging into the ground to provide grip. In the weightless environment of space, there would be no ground to push against in the same way. The cheetah's body would be able to move, but it would likely float and drift instead of running. In microgravity, its limbs would push against the floor or walls of the space station, but without gravity to anchor it, the cheetah would likely be propelled in the opposite direction. This means the cheetah's body would lack the necessary contact force to accelerate in the same way it does on Earth. While a cheetah's muscles are built for quick movements, its acceleration would be very different in space. On Earth, the cheetah's sprinting is powered by its interaction with the ground, but that force is significantly weakened in space. Instead of launching itself forward, the cheetah would essentially push off from surfaces, resulting in a floating motion. It might look more like a bounding leap rather than the iconic sprint we see on Earth. In a low-gravity environment, a cheetah could still demonstrate its agility. Its muscle memory and speed would allow it to make rapid, powerful movements, but it would not be able to reach the same 60-mile-per-hour speed. In fact, without the resistance of gravity, the cheetah might struggle to even reach any significant speed. The biomechanics of running, jumping, and even walking all depend on a stable interaction between an organism and gravity. In the absence of this, animals like cheetahs would have to adjust their movement strategies entirely. Instead of sprinting, they might float or drift quickly, but would lack the direct controlled acceleration of an Earth-based sprint. Microgravity would also affect the cheetah's coordination. On Earth, the cheetah uses its tail to stabilize and steer while running at high speeds. In space, without a stable surface beneath it, the cheetah's tail would not be able to provide the same stabilizing force. This would further hinder its ability to move with precision and control. What does this mean for the cheetah's speed in space? Essentially, the cheetah would be far slower on the ISS than it is on Earth. Instead of reaching 60 miles per hour, it would likely float or drift at a much slower pace, unable to utilize its natural running mechanics. Yet even with these limitations, the cheetah's speed could still be impressive in terms of space movement. If the cheetah were to run on the ISS, it might not hit 60 miles per hour, but it could still cover significant distances quickly, just in a different manner. The cheetah would rely on momentum to travel, and its jumps could carry it across the station, but it would have to adjust to the lack of friction and gravity. Would the cheetah still be agile in microgravity? Absolutely. While it can't sprint in the same way, the cheetah's ability to twist and turn in mid-air would allow it to maneuver quickly in zero gravity. Astronauts on the ISS have to adjust to moving through space using handrails and footholds to stabilize themselves. In a similar fashion, the Cheetah could use the station's walls to push off and adjust its path. But the lack of gravity would make these movements far less coordinated than on Earth. How might the cheetah's body adapt to such a radically different environment? In the absence of gravity, the cheetah's muscle and bone structure might begin to change. Astronauts in microgravity often experience muscle atrophy and bone loss because they don't have to support their bodies in the same way as on Earth. While this doesn't happen immediately, prolonged exposure to microgravity can cause these effects. For the cheetah, the absence of gravity might result in weaker muscles and a decrease in bone density over time, which would affect its speed and agility. It's possible that the cheetah's body would adjust, but this would likely take much longer than an astronaut's adjustment period. Would the cheetah's instincts be altered in space? On Earth, a cheetah's body is finely tuned to chase and hunt prey. Its reaction time, sprinting ability, and coordination are the result of millions of years of evolution. In space, the lack of gravity would disrupt these finely tuned instincts. The cheetah might not have the same drive to chase as it would in the wild. Instead, its instinctual movements could become disoriented due to the unfamiliar environment. This would affect its ability to hunt or escape danger. In terms of hunting, cheetahs rely on their speed and stealth to surprise prey. But in the microgravity of space, these tactics wouldn't be as effective. A cheetah would no longer be able to chase down prey in the same way. However, its powerful senses, such as sight and hearing, would still be intact. If the cheetah were to be placed in an artificial environment, its vision and tracking abilities might still allow it to hunt in a virtual sense. Perhaps future space missions could experiment with using animals like cheetahs in zero-gravity environments to better understand how speed and agility change without gravity. Such experiments could offer valuable insights into how different species adapt to space conditions. Moreover, studying animals like cheetahs in space could help scientists learn more about how humans might adjust to microgravity over time. Would animals like cheetahs be able to adapt to life on a space station in the long term? As with humans, prolonged exposure to microgravity would likely have physical and behavioral impacts on cheetahs. While their speed may decrease, their adaptability might still make them useful in space studies. By understanding how a cheetah's body adjusts, we can gain insight into how all animals might react to the challenges of space travel. In the end, while a cheetah's top speed in space would be much slower than on Earth, its agility and ability to move in microgravity would still be impressive in its own way. And just as astronauts rely on their own ingenuity to navigate space, the cheetah's natural agility might provide inspiration for new ways to move through zero gravity. Though it may never reach 60 miles per hour, the cheetah in space would still remind us of the beauty and adaptability of life in all its forms. Its presence on the ISS could even offer insights into how we can design better systems for movement in space. Perhaps one day, as we explore the stars, we'll discover that speed in space doesn't always come from running. It can come from floating, bounding, and adapting. And in that, the cheetah, a creature of the Earth, might teach us something profound about movement in the cosmos.